you also have a geometric series. So what is geometric series? A geometric series is the following property. Sigma alpha k, k goes from 1 to infinity or to whatever, is geometric. It's a geometric series if the following is true. The quotient of consecutive terms is a constant. Many years later, Newton came along, and then Laplace, and then they had differential equations, and then they had to solve them, and Bessel, and they had lots of so-called mathematical special functions of mathematical physics. The Legendre polynomials, the Bessel functions, the Jacobi polynomials, and so on. And later on, in the 20th century, in quantum mechanics, they came up again. The Legendre polynomial and the Lagrange polynomials. If you solve the Schrödinger equation, blah blah blah, you get them. And they done miraculously. They turn out to have almost the same property, but no longer constant. Now it's a rational function of the index. So this is called hypergeometric series. So hypergeometric showed all over the place. And Euler was the first one to notice this property. But he didn't make up the term. Hypergeometric probably came with Gauss. And then it turned out to have uniform notation for this. Thanks to Gauss, we know by the fundamental theorem of algebra that every polynomial could be factored over the complex numbers. So if you look, if you call this rational function P of k, you can factorize it into k plus alpha 1 times k plus alpha 2 times k plus alpha p. For some complex numbers, alpha 1, alpha 2, alpha p. By convention, they took k plus 1 to be all the time. Because the prototypical hypergeometric series was an exponential function. E to the power x, sigma x to the power k, over k factorial. K goes from 0 to infinity. And indeed, if you look at the ratio of consecutive terms, you get x to the power k plus 1 factorial over x to the power k over k factorial, so you get x to the power k plus 1. So you get x over k plus 1. So k plus 1 happened to be over there. So for the sake of convenience, the denominator always had k plus 1. And then we have k plus beta 1, k plus beta aq. So that's a generic way of factorizing this rational function that comes up in any hypergeometric series. And each of these famous ones, Legendre, Jacobi, Laguerre, Hermite, falls under this property. So let's find out alpha 1, and of course we need an x, because this is monic. So some x. And the notation in analysis for this was this intermediate notation, the PFQ. So this is the standard notation for alpha 1, alpha p. On the top, Q1, no Q, beta. Beta 1, beta Q, semicolon, the two-line notation X. This is the so-called hypergeometric series. That all the functions, well, almost all the functions of mathematical physics fall under them. And usually the P and Q are not so big. And then an analyst, Gauss and Kummer and Dugal, found several, about 10 identities relating them. And so happens that commentators were not aware of this. And commentators, every time they had a commentator thing, they had to do it from scratch, but completely unrelated. And there was the observation of John Andrews and Dick Askew. That combinatorial, and McMahon only knew it, but he didn't emphasize it. For example, this, Dixon. They have the same property. If you take this and divide, you do a Kepler's band, you also get. So every binomial coefficient sum could be written as a hyperdramatic series. So this made life of combinatorics a little bit easier. But still, you needed to prove from scratch the thing. And thanks to so-called WZ, proof theory, each of these things and each of these things is now completely, routinely provable. Just one line comment. But how did it come about? So an important step was due to Bill Gosper, the great hacker that is also mentioned in a different context in the biography of John Conway. And John Conway resents it, gets very annoyed that people think of him as the inventor of the game of life. And John Conway is mostly known in the general public as the inventor of life. And if you want to get on his best side, say, oh, you're the one who invented the game of life. You want to be remembered for other things. So, anyway, Bill Gosper was a great champion a long time ago of making beautiful configuration of the game of life. But he did other things too. He's a true hacker. He's a modern day Ramanujan. He barely, but unlike Ramanujan, who only went to high school, Bill Gosper did make it. He got a D average from MIT. He barely, but of course he never went to PhD. He had too much fun hacking with the computers. He's a major hacker, Bill Gosper. So, has one official paper that got published in the prestigious journal Proceeding of the National Academy of Science. That's because Knuth wrote it up in an acceptable, formal, state way. He wrote the idea and he submitted it because he's a member of the National Academy of Science. So it's 1977. Was a landmark paper of Bill Gosper, a decision algorithm for hypergeometric summation. So geometric summation goes back to Zeno. You can always decide, you can always compute it. To the power n. It's always a closed form. But in Gosper's algorithm, he asks, input a hypergeometric series. For example, 1 over n factorial. People tried very hard to find a closed form answer for this, but they did not succeed. But nobody could prove that it's not possible. Thanks to Gosper's algorithm, we know that this is not summable. You cannot find a hypergeometric sequence. So it is not summable in closed form. Another example, this is also not summable in closed form. On the other hand, exercise for you, this is. And Gosper's algorithm tells you, it's a decision algorithm that tells you whether or not it's summable in closed form, and if it is, what it is. If it's not, it tells you no way. Another example, I can cook artificially.
But go on. A closed form must refer to some restriction on
hyperdramatic, has to be, yeah. You have to be precise. So sigma tk equals some other hypergeometric S of n minus some constant. This is what. In other words, is a solution of this recurrence. Input a hypergeometric sequence D sub n to the exact another hypergeometric. And this beautiful algorithm, I don't have time to tell you the details, and that's not important, it's really a black box. And then you can prove. So just to make up an example where it's positive, I can cheat It goes the other way around. So 1 over n factorial minus 1 over n minus 1 factorial is n minus 1. Right? I hope so. Right? Yeah. So if you didn't do it, so this is sum over. It's 1 over n factorial. 1 over n factorial. Anyway. So that's Gosper. But Gosper hopefully later killed himself. He only did T sub k with some parameter. But now let's go back to the WZ scenario. And he had a decision algorithm where the sequence T sub k only depends on k. And now let's go to the scenario in WZ. In all the binomial, k goes from negative infinity to infinity, that's convenience, equals 1. So all these famous binomial coefficient identities and hyperdramatic could be written in this form. And here how Gosper could have done it if he would have thought about this thing. Never occurred to him to try to use this. Once again, call this A of n. And then look at, and you have to prove that A of n equals 1 for every n, or constant. So n plus 1 minus A of n equals sigma k goes from negative infinity to infinity. F of n plus 1 minus k minus f of n. This is the first step. Now we have two parameters, n and k. K is a summation index. But n is only a silent, n is a parameter. It doesn't do any harm. So what Gosper could have done back in 1977, take each and every one of these famous binomial coefficient identity, form this thing, it's easy to see it's also hyperdramatic, and plug it into the algorithm and find whether there is a solution to this recurrence. So now that we have the n, now with respect to k. So n is not the current parameter. So this thing that looks depends on f and k, n and k. Doesn't depend on two parameters, on two discrete variables, n and k. Think of it as a function, a sequence in k, and ask the Gosper algorithm, the black box, whether this is Gosperable. And sure enough, it always is in all the examples. So you get something. In other words, you solve this recurrence. So this is exactly how it could have been done by Gosper, if we would have thought about it. So this is Bill Gosper's missed opportunity. He could have discovered WZ theory way back. Lucky for me and her Wilf, he did not. So this is how it could be done. Okay, this is very nice. It works on all the examples. In fact, 99.9% of the examples. But how can you prove that it always works? So WZ theory to satisfy the mathematicians also proves it's always possible. In 99% of the cases, you have this recurrence. But in some cases, and in more complicated sums, where there's no closed form, it promises you that you have the so-called Zeilberger algorithm. And the Zeilberger algorithm also based on the Gosper algorithm. And Don Knuth called the Zeilberger algorithm the Gosper Zeilberger algorithm. But luckily for me, and unlikely for Bill Gosper, this name did not catch. So it's now called the Zeilberger algorithm. But maybe it should be the Gosper Zeilberger algorithm. Then again, Gosper did not notice that it's important, so maybe it shouldn't be there. Anyway, if you take anything hyperdramatic in n and k, even something extremely complicated, it's no longer guaranteed to be closed form But the next best thing to closed form is true. Reminding you, closed form means hyperdramatic n plus 1 over an is some rational function in P in n. So in other words, it's a of n plus 1 times P of n minus Q of n, a of n equals 0. So big closed form is equivalent to satisfying a first order recurrence with polynomial coefficients. And the Zeilberger algorithm that is based on Gauss's algorithm, but it's provable that no matter how complicated it is, and even you can make it n plus 3k plus k to the power 20, it's guaranteed to have a recurrence with polynomial coefficients. I don't know, 50 maybe. And if the computer is big enough, you can always find it. And that's a description of the sequence. And together with the initial conditions, you have a complete description of the sequence. In particular, you can always prove that A plus B. If you have another thing like this, you can find the recurrence and initial condition and prove A plus B. So in the remaining 1 minute, let me just tell you the amazing thing that has been done since. First, the theory has been extended by many people. The French school, Frédéric Cizak, and the Chinese school, Bi Chen and Kim Hu and the student, and Xiao Chen and many, many others. But there's another analog of Ramanujan, Jesus Guillard. They gave a talk here about a year ago. Amazing, amazing person. He used the WC proof machinery to find amazing, amazing fast convergence series for pi, or rather 1 over pi. So let me conclude with the Guillard formula. Sigma angles from 0 to infinity. So this is only one of the many applications of WC theory. To get infinite series, extremely fast converging series. So, I'm running out of time, so it's very small here. 2n factorial to the power 5 over n factorial 10 times 20n squared plus 8n, plus 1 over 2 to the power 2n. Check it on the computer. Let's go to Google. Google him, and he has this formula on his web page. Go to Maple and check it. Equals blah blah 8 over pi squared. And you can get 10,000 digits in no time. So this is only one of the applications of WC theory. Thank you for your attention.